One very important idea that came out of the start of the 20th century is the notion that particles sometimes act like waves and waves sometimes behave like particles, also called wave-particle duality. This came about when scientists observed both particle and wave-like properties when analyzing light. For example, light can be described as a wave when it reflects, diffracts, or refracts, like it does in the double-slit experiment done by Young, but cannot be described as such in the photoelectric effect observed by Einstein in 1905. In 1923, Arthur H. Compton observed that when X-ray photons were scattered by electrons, the wavelength, and therefore the energy of the photons, changed, which shouldn't have happened if the X-rays behave as waves. He explained this by treating photons as particles and successfully applying conservation of momentum and energy laws, which meant photons had momentum just like a particle. This discovery led some to wonder if only light behaved this way. In his thesis in 1924, Louis de Broglie postulated that electrons also exhibited behaviors of waves and particles, and proposed that all particles exhibit wave-like properties. He did this by relating ideas of mass-energy equivalence and the Planck-Einstein relationship, by setting E equals mc squared from relativity and E equals hf, the energy of a photon, equal to each other, and by doing some manipulation, de Broglie came up with a hypothesis, aptly called the de Broglie hypothesis, where lambda, the wavelength, equals Planck constant divided by the momentum of a particle, which demonstrates massive particles having wave-like qualities. Initially, the relationship was only meant for electrons, but with time, we know it to be true for more massive objects, like atoms and molecules. The main implication of de Broglie's work is that now matter, previously only thought to exist in particle form, could now also exist in the form of waves. All of these discoveries were fundamental to create a basis upon which quantum mechanics could be built. As we all know from a classical point of view, it is possible to determine both the position and momentum of a particle with absolute certainty at the same time. However, in quantum mechanics, Heisenberg's uncertainty principle, published in 1927, limits theoretically and experimentally our ability to measure with absolute certainty the exact position and exact momentum of any particle simultaneously. More specifically, the more accurately we measure the momentum of a particle, the more inaccurate the position measurement becomes, and vice versa. While one might think this is simply due to experimental inaccuracies, it is important to understand that the uncertainty principle is instead a manifestation of wave properties in quantum mechanics, or in other words, the principle is a limit that we simply cannot overcome. That limit being that the product of the absolute uncertainties in our measured quantities, or the absolute uncertainties of position and momentum, must be greater than half the reduced Planck length. In order to describe the position and momentum of a matter wave, we use a wave function. A wave function is a mathematical construct that describes the wave properties of a particle. If a wave function of a matter wave is, for example, a perfectly sinusoidal wave, then it has a determined wavelength, from which we can determine the momentum. However, since the sinusoidal wave is infinite, we cannot know the exact position, as it could be at any point along the wave. If we, however, consider the same wave for many different wavelengths and superimpose these waves, something like this can be obtained. The red and blue lines you see are the superimposed waves of different wavelengths, and the green line is simply the modulus squared of the function. This is a probability distribution of the possible positions of the wave. As you can see, the area of highest probability for the position is the peak of the green line, which coincides with the most oscillating component of the superimposed waves below it. By superimposing many different waves of varying wavelengths, we no longer have a very accurate value of the momentum of the particle. Mathematically, we extrapolate information from the wave function by collapsing it into an eigenfunction. Each eigenfunction differs based on the initial parameters of the wave function. The eigenfunction to obtain momentum will be, as described above, a continuous infinite wave with a certain wavelength, while the eigenfunction for position will be a function defined for a single point or a range in space. In order to obtain the eigenfunction for one point in space, we must superimpose an infinite number of momentum eigenfunctions, and vice versa for a momentum eigenfunction. Over all space, we must consider all points in space. Therefore, our accuracy for either measurement drops as the other increases. This mathematical way of interpreting the uncertainty principle shows how we can never fully describe either position or momentum of a particle. It is also worth noting that while here we took into consideration the most popular form of the uncertainty principle, there are other forms of it relating different measurements such as energy and time. Werner Heisenberg won the Nobel Prize for the creation of quantum mechanics. However, he based his work on that of others before him. In turn, his discoveries have been used to deepen our understanding of the universe today.